In 1.5.7, we have this switch diagram. So a message comes in and can either go to the top or the bottom. It has a 0.8 chance of getting past box 1, 0.92 chance of getting past, switch 2, and 0.9 chance of getting through switch 3. And it asks, what's the probability that it makes it through? Now, sometimes it's just easier to think about it not making it through. And so let's look at and use the column rule. So the probability that makes it through equals 1 minus the probability that it doesn't make it. And so the probability that it doesn't make it, that would have to be it doesn't make top and it doesn't go through the bottom. And not through bottom. So let's focus on each piece and take a time out. So, and not going through the top. What has to happen for it to not go through the top? For it to not go through the top, either 1 could work and 2 broken, or number 1 could be broken and number 2 could work, or they could both be broken. Okay, let's see. So not through top. Either, let's see, number 1 works and 2 broken, or number 1 works, oh no, that's not one. Or let's see, 1 broken and 2 works, or 1 broken and 2 broken. Either way, it's not going to go through the top if any of those happen, right? So let's add up those possibilities. So we have, working in blue, let's write probability of each broken here. So 1 minus 0.8 is 0.12, 1 minus 0.92 is 0.08, and 1 minus 0.9 is 0.1. Okay, just so we have those. So 1 broken and 2 broken, both, or 1 working and 2 broken would be 0.88 times 0.08. And 1 broken and 2 working would be 0.12 times 0.92. And 1 broken and 2 broken would be 0.12 and 0.08. Now add these all together. So our total would be 0.1904. Now, did you notice how that kind of took a long time to do? There's an easier way. If you want the probability that it doesn't go through the top, find the probability that it goes through the top. So the top works. For the top to work, 1 has to be open and 2 open. So that's 1 works and 2 works. So that'd be 0.88 times 0.92. So 0.88 times 0.92 is 0.8096. Then the probability of it not working is 1 minus 0.8096, which is 0.1904. So notice how either way we got the same answer here. The one way seemed a lot simpler. That's kind of the same idea of what we're doing, why we're doing all this, which might seem like a long process to get to our final answer. It's because we originally want the probability that makes it through. But there's a lot of different possibilities here of like 3 could work, but 1 might not work, or 3 could work and 2 might not work, or 3 works and 1 and 2 don't work, etc. There's so many possibilities, it's often easier to go to the complement. So in this case, finding the probability that the top works, that was easy. Probability that the top doesn't work took a lot more work, so use the complement. But we now know the probability that the top doesn't work is 0.1904. And the probability that the bottom doesn't work, that's easy, that's just 0.1. So let's go down here again. So we said the probability that makes it is 1 minus the probability that it doesn't make it. And for it to not make it, that means it doesn't go through the top and it doesn't go through the bottom. Well, we found each of those probabilities is an n, so we can just times the 2. The probability that it doesn't go through the top, we said that that's 0.1904. And the probability that it doesn't go through the bottom is just 0.1. So this gives me 0.98096.